Welcome back to chapter 23. This is the last of our 3 videos, and we'll look at transformers and wireless charging in this particular video. So a transformer takes electric current and potential and either increases it or decreases it, depending on if you're dealing with step-up transformers, the potential or voltage goes up, or step-down transformers, the potential or voltage is reduced. So any transformer has an iron core with 2 separate wire coils. So you have a power supply. The little wavy line means it's an AC power supply, an alternating current power supply. So the current flows through this coil of wire that's wrapped around our core, this table-shaped part of the drawing is meant to be the core. So this wire is wrapped around it on the left side. That's the primary, the one where the power comes in. The secondary is the output. And so you can see that I have different numbers of coils on my output compared to my input. And this is meant to be maybe your house. So current comes in through the primary. It is induced in the secondary, but because the coils don't match up exactly, there will be a different amount. So the AC current passing through the first coil is going to produce a changing magnetic field, which produces a changing magnetic field in the secondary coil, which gives us our current. Transformers only work with AC current because DC doesn't produce that changing magnetic field. In these, we always call the primary is the input and the secondary is the output. Primary will be the input, secondary will be the output. Power in the primary is going to equal the power in the secondary. Remember, P equals IV, that kind of power. So power in the primary equals power in the secondary, but the ratio of the number of coils in the primary to the number of coils in the secondary is going to equal the potential in the primary divided by the potential in the secondary. You will need to know this equation that N primary over N secondary equals V primary over V secondary. If we want to see, well, how does this impact the current? We can go back to this statement of power in the primary equals power in the secondary and substitute in and rearrange, but the end result will be this equation, which you will also need to know, and that's that the number of coils in the primary divided by the number of coils in the secondary equals the current through the secondary divided by the current through the primary. So you can notice that it looks a little different from the voltage version. In the voltage version, primary and primary were on top, secondary on the bottom. In the current version, if you have primary on top for the number of coils, primary will be on the bottom for the current. I don't care how you keep it straight, you just need to be able to do that. All right, so step up and step down. A step up transformer, the voltage in the secondary is greater than the voltage in the primary. For a step down transformer, it's just the reverse. So when we're transmitting electric power through the grid, we make a choice. Do we want to transmit it at high voltage and a low current, or at a low voltage and a high current? And the option that we picked was to transmit electric energy over long distances at very high voltages, but correspondingly low currents. The rationale was that this would reduce energy loss. There'd be less heating of the wires and you'd lose less electricity, that your energy loss would be reduced. So we can transmit at, say, even 750 volts. But obviously, if your house has outlets that are 110 volts, we have to do something to bring that down, and we use a series of step-down transformers. You've probably seen a transformer, you just didn't realize that's what it was. So let's look at our numeric examples. Looks like this is a little small. I think I'm going to make it a tad larger, maybe to help us out. All right. So if we come down to our example, so we have a transformer. It has 100 coils in the primary and 150 in the secondary. If the input voltage is 20 volts, what's the output voltage? And is it step up or step down? So we know that the number of coils in the primary is 100. The number of coils in the secondary is 150. We know that it says input voltage. So the voltage in the primary is 20 volts. It says what's the output? So that's V secondary. And our two formulas were N primary over N secondary equals V primary divided by V secondary, and N primary over N secondary equals equals I secondary over I primary. Whoa, I did something and it was not what I wanted to do. I apologize for that. It's enough to make a person just a little crazy. All right, so which equation do we want to use? The ones with the voltages in them. So the very first of the two equations. So we will write down our equation. I come over here. So N primary over N secondary equals V primary over V secondary. If you plug into the two equations, plug into the one equation. Number of coils in the primary was 100 and the secondary was 150. So 100 divided by 150 equals 20 volts divided by V secondary. To get V secondary out of the denominator, you need to multiply both sides by V secondary. To move the 100 to the other side, it'll go in the denominator. To move the 150 to the other side, it'll go in the numerator. When you do your math, we end up with 30 volts. Because the output voltage is greater than the input, V secondary was 30, V primary was only 20. This is a step up transformer. It is a step up transformer. So let's look at a second example. Transformer has an input current, so that would be I primary, of 25 amps, an output current of 150 amps. Whoa, my formulas are in the wrong place. Let's get them over here where there we go. So input current is 25 amps, output current is 150 amps, and the number of coils in the primary is 200. How many coils are in the secondary? That's what we want to know. So we pick the equation that has current in it. That would be our second equation. And plug in. Number of coils in the primary divided by number of coils in the secondary is equal to the current in the secondary over the current in the primary. So 200 divided by the number of coils in the secondary would be 150 amps over 25 amps. To get the number of coils out of the denominator, I multiply both sides by it. To get the 25 out of the denominator on the right-hand side, I multiply. That brings it up on the left. To get the 150 out, we have to divide. And when you do the math, you end up with 33.33 coils. It is odd to think of a fractional number of coils. In the real world, you wouldn't have that. We'd have different ratios to deal with this. All right, moving along. Inductance. We want to talk about mutual and self-inductance. Mutual and self-inductance. So we'll start out with mutual inductance. If you have two coils and they're placed near each other, a variable current in the first coil is going to induce a current in the second. We've already talked about this. We just didn't call it inductance. And there's an equation for that. The EMF in the second coil is going to equal negative M times delta I over delta T. Delta I over delta T is the rate of change in the current in the first coil. The EMF2 is the EMF induced in the second coil. And capital M is the mutual inductance. Mutual inductance is measured in henries, where 1 henry is an ohm second. 1 ohm multiplied by 1 second. So the mutual inductance, capital M, depends on the presence of ferromagnetic materials. You may remember those are things like iron or gadolinium or cobalt, and the geometry of our coil configuration. Transformers use mutual inductance. Remember, the two wires didn't actually connect with each other. They were separated. They were just close. So there are other things that use mutual inductors. Some pacemakers are powered externally. This makes it really handy. You don't have to have a wire coming out of your chest to power up your pacemaker. The power in an external coil is transmitted by mutual inductance to a secondary coil in the pacemaker. Another thing, more common probably, is that there's the wireless charging of cell phones. You know, you may have a cell phone that you can just drop on a charging pad. If you have that, what you're using is mutual inductance. There's a little coil inside your cell phone and a coil inside that pad. And it's just like with the transformer. The varying magnetic field in one will produce a current that'll produce a varying magnetic field in the other that will produce a current, and then you can charge your cell phone. It is not very efficient. This form of charging is not as efficient as plugging it in, but some people like it better. I'm sure they'll get more efficient as time goes along. There's another kind of inductance. It's called self-inductance. Self-inductance. So the back EMF, remember, that's the current in a motor that resists the turning. And why when a motor stalls, there is no back EMF and the wires get too hot, and the end result is that you can burn up your motor if it stops turning and you keep trying. So self-inductance, the equation is that the EMF is equal to minus L times delta I over delta T. So capital L is the self-inductance. It is measured in henries. That script E is the EMF for the voltage, and I is current and T is time. So the self-inductance depends again on ferromagnetic material and the geometry of the coil. There are uses for this in AC circuits. You can use an inductor to act like a resistor to impede the flow of current in an AC circuit. Energy can be stored in an inductor. It's stored in the, oh, I overshot, my apologies. It's stored in, well, I've overshot again. Here we are. So energy is stored in an inductor in the magnetic field, and it's not lost or dissipated like the energy given up when in a resistor. So that's one reason you would use it to resist the flow of current. It also can store energy. You don't need to memorize the equations. They're just there to give you some idea of what's going on. You can have inductive reactance or impedance. It would be measured in ohms. So reactance is used to measure only the inductive properties of the coil, and impedance looks at the total impeding qualities. So that's the inductance and any resistance that you're dealing with. And finally, if your resistance is 0, then the impedance and the reactance are the same thing. Why do we care about this? Well, sometimes when you're designing a circuit, you have to match the impedance in order to get it to operate correctly. All right, we will stop with this. The material will end here, so I'm going to stop the share and I'm going to stop the recording.